Okay, so we looked at some initial graphs that showed us the average and the standard deviation of different measurements. And now we want to dig a little bit deeper and look at correlation between the measurements on different days. So the way that we're going to do it is we're going to use the PCA that we computed before and see how we can explain things using the PCA. We'll start it here and we'll continue in the next video as well. Okay, so the first and most important thing to look at is how much do the top eigenvectors explain? How much of the variance of the total variance do they explain? So what we see here is that for T min, T observed, T max, it is modest. It's basically the first one explains about 0.2. And then you get smaller, and then the top 5 explain about 0.3. Here, the top one explains about 0.25, and this explains about, and the 5 top explain about 0.35. And here you see the first one explains about 0.1, significantly less, and then this one explains, the top 5 explain about 0.2. Okay, so this is something that shows you that basically if you take T-obs, you're likely to get a better model explaining the data because T-obs is less noisy. Okay, so T-obs basically, with the top 5 eigenvectors, you can explain 35%, while for the other T-min and T-max, you can only explain 30% or 20% respectively. Okay, so that would be our choice were we to do this. Then let's look at snow depth and precipitation. And here it's quite dramatic, right? Because for snow, we see that 5 explain about 14%. For precipitation, 5 explain about 8%. But for snow depth, 5 explain about 80%. Okay, so by far the most explained by the top eigenvectors, and that is a good situation. That basically tells us that for this signal, basically for snow depth, we can build a pretty good low-dimensional model using the top 5 eigenvectors. So let's see what these eigenvectors look like. So here we have the T min and T max, and we see something, but it's pretty noisy, so let's wait till we see T observed. Okay, so T observed makes some sense. So if we look at the top eigenvector, the one that is marked 0, what does this mean? This is more or less a constant throughout the year. Okay, it's a negative constant. What does that mean? It means that this eigenvector basically explains the overall temperature across the year for a location. Okay, so, or for a year. It basically says if you have a lot of this coefficients, then the temperature all over the year are low, and if it is negative, the temperatures are high, but across the whole year. Okay, so they explain basically the mean temperature. The second one looks, in a sense, the opposite of how the temperature looks, right? It is highest in the winter, over here and over here, and it is lowest during the summer. So what does this mean? And another thing to mention is that it crosses the 0. Okay, so 0 is going here in the middle. So what does that mean? It means that if we take, if we have some kind of average temperature and we add to it some amount of this eigenvector, then we're making the difference in temperature between summer and winter smaller. And if we take a negative, we're making the difference between summer and winter larger. So the first one explains essentially the shift, the average temperature, and the second one explains how much summer and winter are different from each other. So these things make sense. If we look at precipitation, it's very hard to see anything that is meaningful. Okay, so if we look at snow, again, very hard to say something definite. But if we look at snow depth, it is actually very clean, right? So we see that there is eigenvector 1 that looks very much like the overall snow. So that basically means that it is controlling if there's a lot of snow or less snow in that place. The second one, the orange, explains whether the snow is early or late. And the last one explains whether the season of the snow is short or long. So each one of them has a clear interpretation, and we will see this more in the next video. So to summarize, we got data from several station year measurements, and then we calculated the mean and standard deviation for a particular station and measurement. And then we looked at the percentage of variance explained by the top eigenvectors, and we actually plotted the top eigenvectors. Next, what we're going to do is see how we can reconstruct individual measurements, individual years, using these eigenvectors, and what that helps us do. So I'll see you then.